In the vast and dusty annals of paleontology, the origin of flight has long been framed as a binary question. Either an animal could fly, or it could not. For over a century, scientists have looked at the hollow bones and asymmetrical feathers of ancient creatures, trying to pinpoint the exact moment when the ancestors of modern birds conquered the air. But today, we are going to dismantle that black and white narrative. We are going to talk about a discovery that has completely upended our understanding of avian evolution, revealing a gray zone that is as dynamic as it is revolutionary. This is the story of how a set of tiny, unassuming footprints in South Korea told a story that bones alone never could. This is the story of the Raptor's leap. To understand this discovery, we first need to transport ourselves to the Jinju Formation in South Korea. This geological site is a treasure trove for ichnologists. Now, if you are not familiar with that term, ichnologists are the detectives of the fossil world. They don't study the bodies of animals, they study the traces they left behind: footprints, burrows, nests. Unlike body fossils, which show us the structure of an animal after it has died, trace fossils capture a specific moment of life. They are behavior frozen in stone. The Jinju Formation dates back approximately 106 million years to the Cretaceous period. Back then, this area was a diverse ecosystem of ancient lakes and mudflats, preserving the movements of everything from massive long-necked sauropods to tiny invertebrates. And it is here, preserved in the fine-grained mud of a prehistoric lakeshore, that a team of researchers, led by Dr. Kyung-Soo Kim, discovered a trackway that seemed to defy the laws of physics. The footprints were given the scientific name Dromaeosauriformipes raris. That is a bit of a mouthful, but in the dry language of science, it translates roughly to rare footprints with the form of a dromaeosaur. Dromaeosaurs are the family of dinosaurs we popularly call raptors. This is the family that includes the famous Velociraptor and Deinonychus. They are instantly recognizable by the sharp sickle-shaped claw on the second toe of each foot. Because dromaeosaurs held this killing claw off the ground to keep it sharp, their footprints are distinctively didactyl, meaning they show only two toes, the third and the fourth, making contact with the mud. The tracks found in the Jinju Formation were unmistakably dromaeosaurid. They had that classic two-toed impression. However, they were absolutely minuscule. These tracks were left by an animal with feet only about 2.5 centimeters long. That is an inch. This would have been a creature roughly the size of a modern sparrow. Based on the size, it was likely a microraptorine, a subgroup of tiny, feathered raptors. But here is the thing. The size was not the puzzle. We know tiny dinosaurs existed. The puzzle was the spacing. To understand why these tracks caused such a stir, we have to talk about the mathematics of dinosaur speed. In 1976, a British zoologist named R. McNeill Alexander developed a formula that allows scientists to estimate the speed of a dinosaur based on its stride length and its hip height. The logic is simple. Generally, when an animal runs, its stride lengthens. A walking human might have a stride of less than a meter, while a sprinting Olympic athlete covers vast distances with each bound. However, there is a biomechanical limit. Legs can only push so hard and reach so far before biology says stop. When Dr. Thomas Holtz Jr. of the University of Maryland and his colleagues applied these standard calculations to the tiny raptor tracks, the results were nonsensical. The stride length was enormous relative to the tiny size of the feet. The calculations suggested the dinosaur was moving at a velocity of 10.5 meters per second. That is roughly 23.5 miles per hour. Now, 23 miles per hour might not sound like supersonic speed to a human driver, but you have to scale this down. For an animal the size of a sparrow, that speed is ludicrous. If you scaled that up to the size of an ostrich or a cheetah, The relative speed would shatter biological limits. If a sparrow-sized animal were truly running that fast using only leg power, its muscles would need to generate force far beyond what biological tissues can sustain. It would be the equivalent of a human running at highway speeds. So the researchers were left with a distinct set of possibilities. Theory 1, the stilts theory. Maybe the dinosaur had grotesquely long legs, completely unlike any known dromaeosaur. That seemed unlikely given what we know about their anatomy. Theory 2, the missing tracks. Maybe the animal was hopping like a kangaroo, and the preservation conditions failed to record the intermediate landing spots. But the sediment layers were clear and continuous, so that didn't fit either. That left the third, and most thrilling, possibility: the gravity cheat. The animal was generating lift. This leads us to the concept of flap running. This behavior fundamentally changes how we visualize the movement of early feathered dinosaurs. We need to stop thinking of flight as a switch that gets flipped. One day you walk, the next day you fly. Instead, think of it as a hybrid form of locomotion. Imagine an aircraft accelerating down a runway. Before it lifts off completely, there is a moment where the wings are generating significant lift, effectively reducing the weight of the plane on the wheels. The plane is still touching the ground, but it is light. It is skimming. The researchers proposed that the maker of these tracks was doing exactly this. As it sprinted across the Cretaceous mudflat, likely fleeing a predator or chasing prey, it began to flap its feathered forelimbs. We know that dromaeosaurs like Microraptor possessed extensive feathering on their arms, and often their legs, that formed broad, bird-like wings. By flapping these wings while running, the dinosaur created aerodynamic lift. This lift didn't necessarily carry it into the clouds, but it counteracted gravity enough to pull its body upward. This aerodynamic assistance allowed the animal to do three things. First, it increased hang time. With each step, the lift kept the dinosaur airborne for a fraction of a second longer than gravity would normally allow. Second, it lengthened the stride. Longer airtime means the animal travels further forward before its foot must strike the ground again. And third, it maintained speed. By reducing the friction and impact with the ground, the animal could move faster and more efficiently. This behavior turns these footprints from a simple record of a run into a smoking gun for the evolution of flight. It suggests that the transition from ground-dwelling theropods to sky-conquering avians involved a phase of power-assisted running. To fully appreciate this behavior, we have to look at the actor behind the footprints. While we cannot identify the exact species from tracks alone, the morphology points directly to the microraptorines. The most famous of this group is Microraptor gui, discovered in the Liaoning province of China. Living roughly 120 million years ago, Microraptor is one of the most bizarre and revealing dinosaurs ever found. Unlike modern birds, which have a single pair of wings, Microraptor was a four-winged glider. It had long, asymmetric flight feathers not just on its arms, but also on its hind legs. For years, paleontologists debated how Microraptor moved. Did it sprawl its legs to form a biplane wing? Did it tuck them under? Most importantly, was it a tree dweller, following the trees down hypothesis, or a ground dweller following the ground up hypothesis? The trees down hypothesis suggested that Microraptor climbed trees and glided down like a flying squirrel. Its anatomy seemed ill-suited for running on the ground. Long feathers on the legs would presumably trip it up or get damaged. However, the tracks in South Korea challenge the exclusivity of the trees down model. They show a microraptorine moving at high speed on the ground. This implies that despite their cumbersome leg feathers, these animals were capable terrestrial runners. It also suggests that their wings were not just passive gliding structures used for descent, but active aerodynamic tools used for acceleration on the flat. This aligns with a theory known as wing-assisted incline running, or Wei-ai. We see this in modern birds like chukar partridges. When these birds are chicks and cannot yet fly, they use their developing wings to flap furiously, while running up steep inclines like tree trunks or cliffs. The flapping pushes them into the surface, giving their feet better traction. The tracks in Korea suggest a variation of this, wing-assisted running on the flat. The flapping wasn't for traction, it was for speed and stride elongation. It paints a picture of a versatile predator that was comfortable in the trees but lethal on the ground, a creature that used the air as a tool long before it fully conquered it. This discovery highlights how the raptor's leap blurs the lines of classification. We humans love categories. A bat flies, a mouse walks, a penguin swims, an eagle soars. But evolution is rarely so tidy. It is a messy, gradual process of tinkering. The discovery of flap-running tracks confirms that flight was not a singular invention that appeared overnight. It was a spectrum of locomotor behaviors. It likely started with passive parachuting to slow a fall, then gliding, a controlled descent from height, then flap-running, using wings to assist ground movement, which is what we see here, then weak-powered flight, burst flights for escape lacking stamina, and finally, the advanced powered flight of modern birds. The tiny dinosaur in South Korea was operating in the middle of this spectrum. It had the hardware for flight, feathers and wings, but was using them to enhance its terrestrial hardware, legs and claws. This mosaic evolution explains why we see so many experimental dinosaur forms in the Cretaceous. Nature was essentially throwing aerodynamic ideas at the wall to see what stuck. The lineage that led to modern birds was simply the one that mastered the transition from flap running and gliding to sustained, powered flight. I also want to touch on the geological miracle of this discovery. Finding the tracks of a sparrow-sized dinosaur is incredibly rare. Footprints in mud usually wash away with the next rain or tide. For tracks to be preserved, the sediment must be the right consistency. Sticky enough to hold the shape, but not so wet that it slumps. It then needs to be buried gently and rapidly to protect it from the elements. The Jinju Formation is unique because of its fine-grained lacustrine deposits. That means lake deposits. The mud was fine enough to capture the exquisite detail of tiny toe pads and claw marks. These tracks are so delicate that they were likely made on the shore of a drying lake, baked by the Cretaceous sun just enough to harden before being buried. Dr. Kim, Dr. Lockley, and their colleagues had to act as forensic detectives. They didn't just measure distance, they analyzed the depth of the prints. In a normal run, the force exerted on the ground is proportional to speed. A sprinting animal hits the ground hard. But these tracks were relatively shallow for the speeds implied by the stride length. This shallowness was the final clue. The animal wasn't hitting the ground with its full weight. It was being lifted. So let us reconstruct the scene based on this study. It is late morning in the early Cretaceous of the Korean Peninsula. The landscape is dotted with active volcanoes in the distance, but here, by the lakeshore, it is quiet. The air is humid and thick with insects. A small microraptorine emerges from the fern scrub. It is a striking animal, perhaps iridescent black like a crow, with feathers streamlining its body, and a long, stiff tail acting as a rudder. Suddenly, a predator appears, perhaps a larger theropod, or maybe a sudden noise startles it. The microraptorine bolts. It starts with a run, its two-toed feet kicking up small spurts of mud. As it accelerates, it instinctively unfurls its forelimbs. The long flight feathers catch the air. It begins to flap, whoosh, whoosh. With each downstroke it feels a tug upward. Its feet spend less time on the mud and more time in the air. It bounds forward in impossibly long leaps. 1 meter, 2 meters. To an observer, it would look like a stone skipping across water, half running, half hovering. It reaches the safety of a tree trunk and uses its momentum to run vertically up the bark, its claws gripping the wood, wings still beating to pin it against the tree. High in the branches, it looks down. On the mudflat below, it has left a message that will wait 100 million years to be read. a set of tracks that defy gravity. This study is a triumph of modern paleontology. It combines traditional fieldwork with biomechanical modeling to extract dynamic behavior from static stone. It reminds us that the distinction between dinosaur and bird is largely semantic. In the late Cretaceous, the line between running and flying was not a wall, but a ramp. Dinosaurs didn't just look at the sky and wish to fly. They ran toward it, flapped at it, and eventually leaped into it. The tiny tracks in South Korea are the enduring footprints of that leap, proving that long before the first eagle soared, the raptors were already testing the limits of the air. They were the pioneers of the vertical world, and their legacy is the sky full of birds we see today.